All right, guys. So let's get back to now we haven't in a minute, like in several minutes, but let's get back to proving triangles are congruent. All right. So just kind of snap back to the mentality here. If we're going to prove these two triangles are congruent, we have to think about the shortcuts. Okay. AAS, right? And this is when we're going to go ahead and do our formal analysis, but we're looking for different stuff here, and you got to be prepared on the test. You're going to be asked to prove triangles are congruent. You'll be asked to prove all sorts of different things, and so just again, be prepared, be flexible. You're going to be asked to prove a lot of stuff. All right, so let's get into the analysis. And we're only given one thing, and if you notice that the proofs are getting more difficult, we're getting less and less to start with, and so we're told that C, which I'll kind of highlight here in red, is a bisector of AL. Now AL is this line right here. And also NM, which runs the other direction. Now, this is really good news because if C is a bisector for both one, by definition, a bisector, it cuts a lot of stuff in half. And so if C is a bisector of NM, I know that these two pieces are congruent. And I'll even mark here the definition of bisector. Okay. But also, these should be congruent. Notice I'm marking these differently, like I'm putting 2 marks there instead of 1. This is also a definition of bisector, by the way. Okay, I'm putting 2 instead of 1 because even though I know that C is a mutual bisector, I don't know all the pieces are congruent. I just know it cuts the main piece in half. And so if you look at what we have here, we have side 1, we have another side, we have side 1, side 2. And so that really means we have 2 possible shortcuts. Because remember, this one, that one's no bueno. That doesn't actually work. That's the ambiguous case. And so we have to decide whether or not we can find that third side or whether or not we have to find the angle in between the two sides. Well, there's no more given information. I don't know anything about NA and LM. They're not touching C, and so I can't say anything like it's a bisector. They're not overlapping, so I can't use reflexive. I think this is a bust, guys. It's really hard to find side links. Unless you're given something directly like it's a bisector or something, you really don't have much of a chance of showing side lengths. And so I think this is going to be our best bet. Now, if we look at where the A is, okay, the A is located literally in between the two sides. And so if this is side 1 and this over here is side 2, the angle I'm looking for has to be like right here. That's the only thing that gives me side angle side. And so on the bottom triangle, that's the angle that has to happen as well. Now, hopefully you recognize this, but if not, again, the tactic's going to be to kind of redraw this intersection separately. And so there's the 2 intersections, and I'm looking for the angles here. Oops. I'm looking for the angles here and here. Well, hopefully you recognize that as being vertical angles, or the vertical angle theorem, which is how we get VAT. Okay, but those will turn out to be congruent, and so we have side, angle, side, which means we have enough to write a statement of intent now. So to prove the triangle ACN and LCN, the top and bottom triangles are congruent, it looks like we're definitely going to use SAS. We'll meet the side lengths by using definition of bisector. We'll meet the angle by using the vertical angle theorem. I'm going to write right here VAT, or vertical angles. Okay, and so let's get that statement of intent down. So to prove the triangles are congruent, I'll use SAS. To meet the shortcut, I will use the vertical angle theorem and definition of bisector. Short, sweet, to the point. Let's write the proof. And so I'm going to switch it up. I usually write flow proofs for this, but again, just in the spirit of like changing it up and respecting different people's styles. Oops. Let's go. I'm going to write a 2-column proof for this. So like on my test, I don't really care how you write proofs, to be honest. Like you can write whatever form makes the most sense to you. But that's not the case sometimes for SAT, ACT, SAT stuff, right? And so let's vary our style a little bit. And so the first step of this kind of proofing is we have to write our givens. And so we have to say C bisects, what are the 2 lines? LA and NM. LA and NM. So bisects LA and also NM. And so that was given to us. It's important, especially in this kind of proofing, this style of proofing, that you always write your givens first. It establishes it as a true statement in the proof itself, and so subsequent steps will make more sense. In a flow style proof with a statement of intent, you don't really need it because it comes directly from the statement of intent. It's much more organic. But for this style of proof, you're going to do something a little bit different. All right, so let's get into our statements. So we have to use side angle side, and so let's name the sides. And so I'm going to go with NC and CM. NC being right here, and then CM being right there. That's a terrible highlight choice. Let's try it again. NC and then CN. Okay, so NCCM. So let's name it. So the side links. Ooh, stop it, machine. So NC is congruent to CM. And this is going to be because of the definition of bisector, which wouldn't make any sense unless we actually said we have a bisector in our first step. Okay, I'm going to go and name the angles now. So let's switch colors. Let's keep it coordinated, shall we? So let's go pink. Okay, so the second step, and I didn't pre-number my angles, which is not a big deal. I'll just use a three-letter thing. So LCM, which is the angle in the bottom, the angle that starts at L, runs through C, stops at N. So we're talking about this guy right here in the middle, which I'm kind of dotting, is congruent to its upper counterpart. Let's flip up here. ACN. Okay, and that's going to be because of vertical angles. TICAL. Angles. Okay, we just have one set of sides left. So we did the we did the NC and CM, and so we have to name this guy. So the LC and then CA are our last set of sides. So 3LC congruent to CA. We already had it's the same one as the green step, or step 1, so we're dealing with the definition of bisector. Okay, and now that we have our side angle side all marked out, we can make a claim on the triangles, and we should copy the claim from right up here, ACN, LCM. So triangle ACN is congruent to triangle LCN. Is it LCN? LCM, okay. LCM, and the reason being, we just met it right here, the side angle side triangle congruency theorem. Okay, so we met our proof statement. We have a reason why. This proof is officially in the books at about 7 minutes, just under 8. All right, so back to basics here, but this is a vertical angle proof, and so we kind of expect to come back to triangles. And so we have some proofs that build equations. We have some proofs that prove parts of triangles. This happens to be the latter, right? So I'll see you guys in proof number like 8 or 9 or whatever, how many we've written already. Jeez.